Welcome friends, Igor is here, and in this video we will talk about applications of matrices to graph theory. If this sounds too pedestrian, then how about this? We will use the power of linear algebra to prove that Gryffindor is better than Slytherin. This is not a clickbait, so stay tuned. A directed graph, or simply a digraph G, is a structure which consists of two sets, a set of vertices and a set of directed edges, which are simply ordered pairs of vertices. If an ordered pair of vertices vi, vj belongs to the set E of edges, then we say there is an edge that goes from the vertex vi to the vertex vj, and we say that the vertex vj is adjacent to the vertex vi. Here is an example of such a graph. This graph consists of three vertices and the set of directed edges is empty. Here is another example. We still have the set of three vertices, but we added two directed edges. Yet another example, the same set of vertices and we added one more directed edge. Notice that now there is an edge that goes from the vertex v1 to the vertex v2, and there is an edge that goes from the vertex v2 to the vertex v1. A walk in a digraph is a sequence of vertices which has the following property. Each vertex in this sequence is adjacent to the previous vertex. In other words, you can walk along the directed edges and traverse this sequence of vertices in the graph. The length of a walk is the number of directed edges in this walk. Let's look at an example. We have a directed graph with 5 vertices. Let's find some walks from the vertex v1 to the vertex v5. One simple such walk is a walk of length 2. We start with the vertex v1, then we go to the vertex v2, and then from the vertex v2 we go to the vertex v5. Also, there is a walk of length 3. From the vertex v1, we first go to the vertex v4, then the vertex v2, and then the vertex v5. We can also find a walk of length 5. We start at the vertex v1, then we go to the vertex v4, from v4 we go to the vertex v3, then we go back to the vertex v1. As you see in the walk, it is possible to return to one of the vertices you already stayed at. From the vertex v1, you then go to the vertex v2, and then finally to the vertex v5. Of course, these are not all possible walks from v1 to v5, but this shows different ways that you can travel along the graph to go from one vertex to another vertex. Now, let's define the notion of an adjacency matrix of a directed graph. Suppose we have a digraph and the set of vertices includes n vertices, v1, v2 through vn. The adjacency matrix of this graph is a square matrix of size n, which has the following property. The entry of this matrix in position ij is equal to 1 if there is an edge from the vertex vi to the vertex vj, and it is equal to 0 otherwise. Let's look at an example of this digraph with 5 vertices, and let's construct its adjacency matrix. This graph has 5 vertices, therefore the adjacency matrix is a matrix of size 5 by 5. To construct the adjacency matrix, you need to define some kind of ordering of the vertices, and in this case, this ordering is naturally given by the indices of the vertices. So we think of the vertex v1 as vertex number 1, and so on. There are only 2 edges that go from the vertex v1 to the other vertices. It's an edge from v1 to v2 and an edge from v1 to v4. Therefore, we have 1s in the second and the fourth position and 0s everywhere else. The second row of the adjacency matrix counts edges that start at the vertex v2. We see that there are only 2 edges that go from the vertex v2 to other vertices. It's an edge that goes to the vertex v4 and an edge that goes to the vertex v5. So we have 1s in the 4th and the 5th position and 0s everywhere else. In a similar fashion, we construct a row that corresponds to vertex v3. Again, there are only 2 edges that start at v3. They go to the vertex v1 and the vertex v4. For the vertex v4, there is an edge that goes to v2 and there is an edge that goes to v3. And for the vertex v5, there is only one edge that goes to the vertex v2. Notice that if I only gave you this adjacency matrix, then you would be able to reconstruct the graph picture on the left. Therefore, in fact, the adjacency matrix contains all the information about the graph. You may ask, what's the use of the adjacency matrices? Why would you go through this procedure of constructing this matrix if you can simply look at the picture of the graph? Well, let's figure it out. For example, if you take row I of the adjacency matrix and you add up all the entries in this row, then this will give you the number of edges that start at the vertex vi. But a single edge that starts at the vertex vi is the same as a walk of length 1 that starts at the vertex vi. So you can use the adjacency matrix to quickly count the number of walks of length 1 that start at any given vertex. For example, if you take vertex v4, you look at row number 4 and you see that there are exactly 2 walks of length 1 that start at the vertex v4. You may say that this is not persuading enough because you can just as easily derive this information from looking at the graph. Well, how about walks of length 2? Suppose we want to count the number of walks of length 2 that start at v1 and end at v5. Of course, you can just look at the graphical representation of the graph and quickly conclude that there is only one such walk, v1, then v2, then v5. So why would you need adjacency matrices in this when you can answer all these questions by simple visual inspection? Well, the visual inspection works fine as long as you have few vertices. But what if your graph contains thousands of vertices? Then that visual inspection method is not quite usable. However, we can quickly and efficiently obtain this number by using the adjacency matrix. Suppose we have a digraph and the set of vertices of this digraph is the set which consists of elements v1, v2 through vn. Let A be the adjacency matrix of this digraph. Then the number of walks of length k that start at the vertex vi and end at the vertex vj is equal to the entry in row I, column j of the kth power of the matrix A. Let me explain why. Let's start with walks of length 2. A walk of length 2 from vi to vj looks as follows. From vi, you go to some intermediate vertex vr, and from that vertex vr, you go to the vertex vj. So let's count the number of these walks when the vertex vr is fixed. This walk of length 2 consists of a walk of length 1 from vi to vr, and then another walk of length 1 from vr to vj. But walks of length 1 are the same as directed edges in the graph. And the number of directed edges from vi to vr is equal to the entry in position IR of the adjacency matrix. Do you see why? The number of these walks is either 0 or 1. There could be a directed edge from vi to vr, in which case there is exactly one walk of length 1, or there could be no directed edge from vi to vr, in which case the number of such walks is 0. Same reasoning applies to the number of walks of length 1 from vr to vj. The number of such walks is the number of directed edges from vr to vj, and this number is the same as the entry in position rj of the adjacency matrix. This number is either 1 if there is an edge or 0 if there is no edge. Now, the number of walks of length 2 from Vi to Vj that pass through the vertex Vr is equal to the number of walks of length 1 from Vi to Vr, which is AIR, multiplied by the number of walks of length 1 from Vr to Vj, which is ARJ. Therefore, the total number of walks of length 2 from Vi to Vj that pass through the vertex Vr is equal to AIR multiplied by ARJ. But this counts only walks of length 2 that pass through the fixed vertex Vr, and this vertex Vr could potentially be any vertex in the graph. Therefore, to count all possible walks of length 2 from Vi to Vj, we add up all the possible walks of length 2 over all the possible intermediate vertices Vr, and there are n such vertices. But now you should recognize that this expression is exactly the entry-by-entry formula for the entries in the product matrix. We multiply matrix A by matrix A, so we take row I of the first copy of the matrix A, we take column J of the second copy of the matrix A, and this expression is the entry in position I, J, of the product matrix, and the product matrix is the square of the matrix A. So this proves that the number of walks of length 2 from Vi to Vj is equal to the entry in row I, column J, of the matrix square of A. Next, let's look at walks of length 3. A walk of length 3 consists of a walk of length 2 plus a walk of length 1. And we can choose some intermediate vertex Vr. So this walk is a walk of length 2 from Vi to some vertex Vr plus a walk of length 1 from Vr to the destination Vj. But we already know how to count walks of length 2. The number of such walks from Vi to Vr is equal to the entry in row I, column R, of the matrix A squared. Also, the number of walks of length 1 from Vr to Vj is equal to the entry in row R, column J, of the adjacency matrix A. And so this tells us the total number of walks of length 3 from Vi to Vj. For this, we simply add the number of walks for each fixed vertex Vr. But now again, you should be able to recognize that this expression corresponds to the entry-by-entry formula for the entries in the product matrix. We multiply the matrix A squared by the matrix A, and therefore this is the entry in row I, column J, of the matrix A cubed. And now you can extend this argument by induction to prove that this also happens in case of a walk of general length k. If you know the method of mathematical induction, it would be a nice simple exercise to construct this proof. Let's apply this result now to count the number of walks of length 2 from one vertex to another vertex in our graph. For this, we take the adjacency matrix and we compute the square of this matrix, which means we multiply the matrix by itself. Now, looking at the product matrix, we can conclude right away that, for example, there is exactly one walk of length 2 from V1 to V5. For this, we look at entry in row 1, this is the starting point of the walk, and column 5, this is the ending point of the walk. Also, we can conclude that, for example, there are exactly two walks of length 2 that start at V2 and end at V2. Let's do this for walks of length 3. For this, we need to compute the cube of the adjacency matrix, and to do it, we take our previous computation, we know what the square of A is, and we multiply this matrix by another copy of the matrix A. Looking at this matrix, we can conclude that, for example, there are 4 walks of length 3 from V4 to V2, and there are no walks of length 3 from V5 to V5. Now, you should be able to see the power of this method because looking at walks of length 3 might be quite cumbersome even for this small graph with only 5 vertices. But enough this technical talk for an abstract graph, let's do something interesting. Let's determine the winner of a Quidditch tournament. This is a round-robin tournament and 5 teams participated. Team Gryffindor, Team Hufflepuff, Ravenclaw, Slytherin, and All-Star Muggles. The results of the tournament are shown in this table. So the result of any given match is given with respect to the row player. For example, Team Gryffindor won the match against Hufflepuff, they lost the match against Ravenclaw, and they won their matches against Slytherin and All-Star Muggles. The question is, who won the tournament? Clearly, we count the number of wins for each team, but we see that there are some ties. Both Gryffindor and Slytherin have 3 wins, so we might be inclined to say that they both tie for the first place. But you know that this is not what any of these teams would want, so can we break the ties? Team Gryffindor claims they won the tournament because they beat Team Slytherin in a face-to-face match. This is called a direct win, and it's a fairly valid reason. But you know Slytherin, right? They claim they won the tournament because they beat Team Ravenclaw, so they better than Team Ravenclaw, but the Team Ravenclaw beat the Team Gryffindor. This is called an indirect win. So, let's be objective and impartial, and let's count both direct wins and indirect wins. And to do this, we are going to use the machinery of linear algebra. At this point, it is not clear at all how graphs come into play here, but let's see. Let's construct what is called a dominance graph. The vertices of the graph correspond to the teams, so there are 5 vertices, and directed edges correspond to direct wins. For example, Team Gryffindor beat Team Hufflepuff, so there is an edge that goes from the Gryffindor vertex to the Hufflepuff vertex. This is a directed graph, and we can construct its adjacency matrix A. Notice that this adjacency matrix can be obtained from the tournament table by replacing every win with a 1, every loss with a 0. Also, because teams do not play against themselves, the crosses are replaced by zeros. Our goal is to count the number of direct wins and the number of indirect wins for each team. But in terms of the graph, the number of direct wins is the number of walks of length 1 that start at the given vertex, and the number of indirect wins for a team is the number of walks of length 2 that start from this vertex. For example, for indirect wins, Slytherin claimed an indirect win over Gryffindor because you can go from Slytherin to Ravenclaw and then from Ravenclaw to the Gryffindor. It is a walk of length 2. To count the number of walks of length 1, we just add the entries in every row. And this corresponds to direct wins. This is exactly what we saw from the tournament table. For example, Team Gryffindor has 3 direct wins, Team Hufflepuff has 1 direct win, and so on. But now, let's also count the number of indirect wins. These are walks of length 2, so we take the square of the adjacency matrix, and to count the number of walks of length 2 that originate at any given vertex, we simply add up the entries in the corresponding row. So, we take the number of direct wins for each team, we take the total number of indirect wins for each team, and we add them up. And now you see that Team Gryffindor has 8 direct wins plus indirect wins, while Team Slytherin has 7 direct wins and indirect wins. So, it is our mastery of linear algebra that allows us to see through the shenanigans of the Team Slytherin and prove that Team Gryffindor is the best. Go Gryffindor! You know, I just realized that it's kind of odd that I was rooting for Team Gryffindor all the way along rather than for my native team of all-star muggles. What about you? If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. As always, I hope to see you later infinitely many times.